Yes. All right, hello everyone. So I do research in neurovision-based systems, and as you guys know, there are a lot of neurovision programs. There's NEAT, INT, cosine, MOGART, mean-guard. There's like thousands of them, and they're all excellent. And what I've been trying to do, I've been looking when I started this research, and trying to find a programming language that conceptually maps one-to-one to the field of neural network-based research. Because, you know, procedural languages, object-oriented languages, they don't have the same, neural networks are basically, distributed graphs, right? And our standard languages are not like that. So I want to discuss the jump the hooks between the language things. So this presentation is based on, I want to present basically that what kind of language you would like to have if you were designing from scratch and apply it towards neural network research. And then this language already exists, and it's called Erlang. And then give you a case study of the system I built in Erlang. It's called DXNN, which seems to be, it seems, the first Erlang-based, neurovision-based system. Right, so I'm going to first briefly introduce neural networks. Then, like I said, how do we create a perfect neural network programming language? And then discuss Erlang, which was created for communications networks. And that is to now be used with neural networks, and then provide you with a case study and what the future should be expecting in this kind of system. Right, then the objectives, of course, elaborate on why Erlang is such a great fit for this research field. Discuss, we firstly implemented such a neural network-based system, and promote the language within the field, because there are a lot of people using it. For example, in Kent University, they're already using it. But in USA, still very few people are actually using Erlang within the classroom and academia. So it's kind of turning towards that. Right, so neural networks, they're basically just a concurrent distributed graphs composed of simple processes that process signals. These are, the first one is a feed-forward neural network, and the second one is a recurrent one. The arrows are just signals passed from outside to the neuron, which does some processing of that signal and passes out output to other neurons connected to it. A neural network-based agent is again a neural network with sensors which interact with the environment and get the information from the environment, pass to the neural network, which processes the signals, and which then forward to actuators which act upon the environment. Now, as we know, the hardware has been, improving and been scaling sideways. We've been increasing the number of cores rather than increasing the speed. So right now, it's actually a perfect time, to implement these kind of distributed artificial intelligence-based systems, because we have these now existing hardware that is fully distributed, and we can take advantage of that if only we had a programming language that utilizes this, and artificial intelligence systems which are based on concurrency and distribution. In fact, one of the recent hardware developments is from Intel, which are releasing a coprocessor of x86-based cores, which in each coprocessor will have 50 plus cores. So it's we're at that time we can really utilize that kind of a system. Right, so the common programming languages, are C++, C, Java, Python, Perl. As mentioned when we, again, discuss neural networks, which are graph distributed systems, they don't have the same architecture. We have to first we have to think like, okay, so this is what a neural network is. We have to I want to have these features, then we go towards C, or C++, or Perl, and then we develop it, and we go back and forth. And that's sort of, especially due to linguistic determinism, sometimes we start thinking in C, like you're just basically thinking that particular language you've been using for years. And, you tend to, imagine kind of things that are not in that language. So if we were to develop a neural network programming language from scratch, what kind of features would it need to have? Well, an interesting list by Professor Dacker is of the following. It should be system must be able to handle a very large number of concurrent activities. Obviously, neurons are all concurrent. Actions must be performed at a certain point in time and within a certain time. systems may be distributed over several computers because we want these to be distributed not just over a number of cores or CPUs, but perhaps even globally or multiple machines. And obviously, the brain is composed of 100 billion neurons with trillions of connections, so distribution is important. Finally, the system is used to control hardware because, well, the implementations, the applications of these computation intelligence systems are robotics, right? UAVs and so on. So it's important that this type of programming language can readily interface with hardware, so you can develop drivers. The software systems are to be expected to be very large in the future. Right now, our neural networks are basically 100, 1,000 some for certain applications, but we expect to grow. The system must exhibit complex functionality, so it should be in continuous operation for many years. Like the rovers, we want the systems to, be very robust, fault tolerant, so they can operate continuously. Especially with computational intelligence systems, UAVs, the system should also be, we should be able to rewrite the source code and then update the system without taking offline, which is also actually one of the main goals in the computational intelligence, that the system can rewrite its own source code, update itself. I mean, this is like, basically the dream of artificial intelligence, one that can rewrite itself. So it should be able to do code hot swapping. Rewrite source code, update itself, done, without going offline. And finally, of course, fault tolerance. What is surprising is that Dacre was not talking about neural network-based intelligent systems. He was talking about telecom switching systems, which apparently have exactly the same functionality and requirements. And Erlang was created for that, which is a great fit. So Erlang has all these features. It has encapsulation primitives, it has concurrency, fault detection primitives, location transparency, which means any neuron can contact any other neuron. It doesn't need to know that the other neuron is another CPU, another machine, or another anything. Only needs its ID, which means we can distribute them over the entire internet and wouldn't matter to it. And has the dynamic code upgrade that I mentioned. It can rewrite itself. It was made to interface with numerous drivers, to create drivers to interface with hardware, because the telecom switches are needed for it. It even comes with a set of libraries, like the stable storage called Amnesia. They forgot A. It's a robust distributed database where you can store anything, and even when the system crashes, it still retains everything, and you can just back it up. And of course, it has already built up infrastructure with many applications. So there is such a language, and it's Erlang. The conceptual mapping that I mentioned is demonstrated here, and it's one-to-one. I mean, I'm actually quite surprised that nobody's using it so much in this area. Every neuron is a process, every sensor is a process, every message is a message, and every actuator is a process. It can be either a driver interfacing with hardware or simulated actuator or simulated sensor. So the mapping is perfect. So, interesting enough, like I said, I was ended up being the first one to use this language. I was trying to figure out why. Maybe I'm just not seeing something. And so I even was able to write a book on it. Also the first one, all right. Anyway, so here's the system is called DXNN. It's a new evolution-based system. It's a parameter and topology evolving universal learning network. So I'm going to give you a brief description of what the new evolution is. You basically create a seed population of very minimal neural networks. You apply them to some problem. It can be artificialized, so they interact with other systems. Or they try to predict something. Then you give them fitness scores. From that, you select the most fit of the agents, and you mutate you create offspring from them by mutating them or using them two or more, using crossover and creating offspring, and apply it again and again and again, finally refining and growing these, vast networks that perform better. In a DXNN system, again, everything is just, there's a diagram, every little, figure there, it's a single process, so everything is self-contained. The neural network-based agents are as follows in the system. We have sensors, actuators, neurons. I added a small system called Cortex, which is basically just a synchronizer for the whole system. Why do you need it is because, for example, let's say you want to put the whole system on pause, right? The way you do it is you make sure that the actuator, after it acts upon the environment, sends the cortex the sync message. At which point the cortex can decide whether to pull all the sensors to action or not. If it does not pull all the sensors to action, then the system is stopped because the sensors no longer gather information. So the whole system is on pause, and during this time, which means the system is not functional, you can sort of mutate it or do something to it. And finally, there's the exasol process, which is very interesting. It's actually used to monitor because Erlang allows each process to monitor every other, which increases the robustness. Because if one process crashes, it can, basically call it again from database or something. And in this case, exasol does exactly that. It monitors the whole neural network. It's external to the system, and it monitors it, and is the one that performs local optimization of the thing. It can contact cortex cell to stop the system from functioning, then perturb some neurons. It has a global view of the whole system, so you can perturb some neurons, tell the system to function again, and start reporting, fitness scores. The whole architecture of the system looks as follows. We just have the infrastructure called Polis, which when you start it, basically just calls the database and all the common environments shared by all the agents that are independent of the agents. And then to perform the experiment, you basically just summon population, which creates species, create agents, and which then begin interacting with the environment. What is actually interesting, the most interesting part of this, is what Erlang allows you to do with a single neuron. Here's a diagram of a neural processing. We have here, of course, the input signals coming towards the neuron. The neuron has a synaptic weight. It weighs the incoming vector. Then it has a signal integrator, activation function, and here we have post-processor and plasticity. Now, with Erlang, the whole thing is basically here. You can give each module a list of different, preprocessors, signal integrators, activation functions, and execute that one function and select dynamically these different things, which means each neuron can have different one of these, and it doesn't matter where there's it's just called out after the fact, which is, it's very difficult to do that in other languages so dynamically and so simply. Even with plasticity, you just, again, do the same thing. Which also allows us another thing. Let's say we have started our experiment, right, and we have already a list of constraints for our population. The constraints means what kind of activation functions, what kind of plasticity functions the system can use, the new created neurons can randomly have when they're just being generated in the new offspring. If we later on, for example, come up with a new type of function, we simply add it to the list. And as the system continues to evolve, the new agents will integrate these new functions into themselves dynamically. Here, for example, we have a standard neuron. It's a post-process is none. We don't post-process the signal. Activation function is sigmoid, which is a standard one. And preprocessor is, again, can be none in this case. And the signal integration is simply dot product. So we take the dot product of the input, the weights vector, and pass it to the sigmoid as a standard neuron. Here, on the other hand, using exactly the same system, we have a completely new type. It can evolve, anybody familiar with the attention resonance theory-based neurons. Here we have a post-process as a threshold. It basically specifies whether the input signal is in a particular cluster or not. Activation function is none. Signal integration is the difference between the weight vector and the input vector, which shows how close the input vector and the weight vector are. And finally, we normalize the input and weights. So you can evolve these completely general things, which is not currently done in any other system. And in Erlang, it's trivial. Just a line of code. So as mentioned, you can easily add new functionality by just adding stuff to the list or removing it. While the system keeps running, you can literally evolve the list as it goes along. Mutation operators are applied in a single line, list comprehension. same way you apply topologies. It already has all the graph, and here's the implementation of a main neural loop. It's under 80 lines of code. And it not only does everything mentioned, it can sustain Darwinian evolution, it can use Lamarckian evolution, it uses neuroplasticity, it uses modulated neuroplasticity, all in under 80 lines, which means you can continue extending it. Actually, it's still understandable, the whole system, because it's so concise. Finally, this is the genotype is based on standard records, which, of course, Erlang has. Erlang has a robust database, Nisha, so you can store all that in already provided. Everything is within Erlang. And here's the genotype of a single neuron agent. Just a set of records. Very easy to understand, very easy to read. And if you ever dealt with a neat or int or others, they have very trying to optimize everything. And it's very difficult to read their genotypes. So you don't really understand when you're simply looking at genotype what kind of agent it is. So, because of all of this, in the future we can expect to continue shipping neural networks over the entire internet. It will be trivial in this language. This adds obviously enormous amount of robustness, Skynet. Erlang's natural code class swapping gives us the ability. This is probably one of the only languages which really allows us to experiment with the artificial life experiments where neural networks can rewrite themselves. And if they make a mistake, if they crash the whole thing, the exoself process, for example, would revert it back to a functional program and try again and again and again. So agents can experiment with rewriting their own source code. And it's already being done. Obviously, building modular neural networks is very simple. Everything is just a process. The application to others. Modular network will be composed out of hot-filled networks and so. In conclusion, common programming languages do not have the architecture that is perfect for neural network programming. Erlang does. It's quite excellent. It's important to, I think, promote this language because it's not being used, it's not being utilized, and it makes things a lot simpler within the field. And I think you leave open a lot of horizons within this research field. And that's it. Any questions?
Questions? So do you know of a way to model a Haskell program, write it in Haskell and then run it on Erlang? Because in Erlang you don't have your type safety and stuff.
That's true. Yes.
But did you find it nice and easy and did it okay without the types?
Yeah, it's fine. I mean, as long as it's interesting. Yeah. You can download the source code. You can download the source code. The whole thing is functional on GitHub. Just type in DXNN and it's there. Yes.
I was wondering how large your program is. A node, it can be enormous, because it's something like 2 million processes. But how many nodes, how many VNs did you use? And did you use a distributed
Can you repeat the question?
So the question is, how many VNs, how many nodes, and how many computers did you use?
I experimentally performed from 1 neuron to 1,000 neurons in a life experiment. Machines used I used from a single computer with a quad core to 10 machines, each with 8 cores, 2 CPUs of 4 cores, and it's all functional. But you actually raise a good point. As all of you who from Erlang know, Erlang's efficiency comes from small messages, large computations, and in neurons, these messages are very small. I mean, the messages are relatively large, and the computation is small. But that's not the case when when the neurons evolve. For example, when you add plasticity, that's a lot of computation, and the neuron becomes very, powerful and can learn from the experience. So, as you start adding more advanced structures to the neuron, they begin processing more information, and so the ratio of processing to signals is becomes in your favor. But you're right, it is slower than something would be written in C. But it's still readable.
So is distribution easy? How could you just say, okay, well, I'll just grab those 200 servers that are lying around, and how can you easily, how do you say, acquire new servers and take them into your service and take them over to grow your network?
Yes. The language provides all that. Yes.
I presume the predominant language used in this area is C or C++. So how does it compare in sort of lines of code to your implementation? So to give us a
Well,
feel.
this particular implementation, it has a lot of too much other stuff, so it's difficult to compare. But it's by order 20 times smaller when you use the same functionality. It's 20 times smaller roughly, and distributed at the same time, and can utilize any hardware with more cores just in.
Okay, thank you very much.
Thank you.